All right, everyone. Welcome to another Waterloo Wellington FIRST workshop. My name is Terry Fisher. I'm a mentor from the 2702 Rebels. And this presentation is on motors. It's not going to cover all of the details that you might want to cover with motors, but it will cover some of the important information for motors, especially with motors you deal with in FRC, and specifically the motors that you're allowed to use this year in the ELIGU challenge. So we have a few different types of motors that are very common. We have AC motors. I'm not sure why my presentation just switched to going line by line here, so you'll have to bear with me as some of these bullet points come up. But we have AC motors, and AC motors would run off of alternating current, and there's a couple types of those. There's an induction type, and those are brushless motors, and they'd be the types of motors that you'd see in the pump in your dishwasher, or a fan in a dehumidifier, or in a washing machine. And they're very, very common motors. They're very easy to manufacture, and they're very reliable. There are also brushed AC motors, and those would be the types of motors that you would find in something like a power tool, so a corded drill or a circular saw or something like that. We have DC motors. That's more like what we would use in FRC. And again, we have the brushless type. They're very similar to AC induction motors. And we have brushed motors. So the basics of an electric motor, they convert electric current into rotation. When electrical current flows through a conductor, it creates a magnetic field. And you can actually tell which direction the magnetic field lines are going around a conductor by taking your right hand and pointing your thumb in the direction of the current, and your fingers will point to the direction of the magnetic flux lines. Most people know that if you take two magnets and you put the north and south poles together, they attract. And if you put the two north poles or the two south poles together, they repel each other. Basically, the way that motors generate rotation from electrical fields is by using the magnetic fields that are generated by the current flowing through the wires to create motion. In DC brushed motors, they energize the magnets in the rotor to cause rotation. The speed and the torque of the motor is controlled by the amount of current flowing through it. In DC brushless motors, there are generally three sets of magnets in the stator, and I'll explain what a rotor and a stator are in a slide or two. And basically, they activate the three magnetic fields in sequence, and that causes the rotor to turn. And the speed of those motors is controlled by the rate of the field change. So the faster that you cycle through the three magnetic fields, the faster that the motor will turn. AC induction motors are very similar to the DC brushless motors in that they use the alternating current to magnetize or to energize the magnetic fields in the stator. They are a little bit different because they already have varying current, so they don't adjust the speed of that. AC induction motors are always running at a speed that's based on the line frequency and the number of poles in the motor. AC brushed motors are probably the most complicated motors to wind because they need to not only have electromagnets on the stator or on the rotor, but they need it on both, because they need to have the stator and the rotor fields changing in order to provide the rotation. So I've already mentioned that there's two parts to an electric motor, key parts. There's also a couple of others. So there's a housing, and there's a stationary magnet usually somehow attached to that housing, and that's called the stator. Sometimes the stator is an electromagnet. Sometimes it is just a permanent fixed magnet. Then there's also a rotating magnet called the rotor. And again, depending on the motor, the rotor can either be an electromagnet, or it can be a fixed permanent magnet. Motors that have brushes would have contacts somewhere on the rotor, and that allows for the current to come into the rotor from an external source, and the brushes just simply slide along a conductive surface. Depending on the type of motor, those brushes either run on rings or more likely on tabs that the brushes will slide across. Another important thing to talk about before we get into the details of motors is what is torque? Because when we talk about motors, one of the important features of motors or specifications is torque. So torque is a measure of rotational force. If you look at the diagram, we have a 100-ounce weight, and I'm sorry for anyone who is far younger than me and is more likely to use the metric system. But I'm still old school, and I think more in terms of the imperial measurements for torque. But we have a 100-ounce weight on a 2-inch diameter or 1-inch radius spool. So basically, to find the torque that is being applied there, if there was a shaft down the center of that circle, and that weight was being held stationary, there would be a torque of 100 ounce-inches applied there. And as I mentioned before, there are a lot of different units that you can use for measuring torque. The typical units are Newton meters, Newton centimeters, ounce inches, foot pounds or pound feet. If you're into cars, you would have heard of engines being specified in pound feet of torque. But we also have kilogram centimeter, kilogram meter, and the list goes on and on. You can even get down into very small ones. If you're dealing with gram millimeters, you're talking about very, very, very small units of torque. So for a motor to lift, in this case, or actually to hold that 100-ounce weight, it would need to be exerting 100 ounce-inches of force. And if you wanted to cause that weight to go up, it would need to be exerting more than 100 ounce-inches of force. And if you have a motor that you're trying to use for something like this, where you want to move a 100-ounce weight on a 1-inch diameter spool, and you had less than 100 ounce-inches of torque, you would have to either do some gearing to improve the torque, reduce the rotation speed, reduce the spool diameter, or figure out how you can move less weight. DC motors have specs in, if you go online to look up details about a motor that you're trying to purchase for something. So the specs for the motors would include either free speed or no load RPM. And that is the rotational speed of the motor without applying any load. So if you just simply hooked it up to its power source out of the box without connecting a pulley on it, gears or anything, as is, that's how fast the motor would spin. Stall torque, as you might get from its name, is the amount of load or the amount of torque that the motor can exert before stopping, being prevented from rotating. Usually, and in fact, in most cases, it's a very linear relationship between load and RPM. So with no load, a motor will spin at its no load RPM. And as you add load to it, increase the load, the RPM will drop until you get to the point that you've reached the stall torque. And another spec that's really important is power. So that's the rate of doing work. And when a motor's power is specified, that excludes the heat that's generated from the motor itself. Motors aren't 100% efficient. And in fact, when the motor is spinning doing nothing, there's no load, so it's not doing any work. So all of the electricity that's going into it, it will be drawing some current. All of that energy is being converted into heat. Likewise, when a motor is stalled, it will be using an awful lot of current, and it also won't be doing any work because even though there's a load, it's not doing anything with that load. It can't actually move it, so it's not doing any work. And in this case, the motor will be getting very, very warm. The peak power from a motor, from a DC motor, occurs when it's running at about 50% of its free speed or no load RPM, which is the same point as it's running at about 50% of its stall torque. And anytime that we're designing a mechanism that uses a motor, it makes sense to try to design it for that peak power. So if we're trying to move a 100-ounce weight, then we would design the gearing so that the motor would have about 200 ounce-inches of torque, or would be able to apply 200 ounces of force. And then there's also usually specs for free and stall current. And as I've mentioned before, the free current would happen when there's no load. That's usually not a it's usually a fairly small number. And the stall current is a very large number. And as the motor is running, a different ratio of that current that's going into the motor will be converted into actual usable power, and that occurs, as I said, at about 50% of the no load RPM or 50% of the torque. This is a very typical power curve for a motor. As you can see, the yellow line is the amount of stall, or is the left is the stall torque. Along the bottom is the RPM, and the yellow line is the torque. So as we gradually reduce the torque, the RPM goes up. And the reason that the graph is done this way with the stall torque at the left is because they started with the speed at 0. And you can also see other numbers that are on there. We have the current that's being consumed, which is also very linear. And we also have an efficiency number. And so the efficiency, percent efficiency, that is how, what percentage of the input power is actually being converted to output power. So the motors that we have access to this year for the Iligu Challenge are the DM-S0090D-R servo, and that is the continuous servo. It has a mass of 9 grams, so it's fairly light, and it has a no load RPM of, wait a minute, servos are spec'd in a funny way. They generally spec servos as an amount of time to turn 60 degrees. And the spec for this particular servo is to turn 60 degrees in 0.1 seconds. And that's at 4.8 volts. This particular servo we could run at 6 volts, and it has, it'll turn a little bit faster, but the power supplies that we have are around 5 volts, so we'll use the 4.8 volt specs. If you do the math on this, to turn one rotation, so 360 degrees, would take 0.6 seconds, which works out to 100 RPMs. The stall torque is spec'd at 1.5 kilograms centimeters. That means that if we had a shaft that was 2 centimeters in diameter, this motor would be able to support a 1.5 kilogram weight. Anything less than 1.5 kilograms supported off of a 2-inch diameter shaft, or 2 centimeter diameter shaft, and this motor should actually be able to lift that weight. And for power, we can calculate by taking the torque and the rotation speed. And servo manufacturers kind of cheat. And FIRST also uses this calculation when they put limits on servo power. And the power that they use is actually the no load RPM and the stall torque. So it's about 4 times the actual torque that you would see, because we normally get our peak power at 50% RPM and 50% of the stall torque. So for these motors, it works out to 1.65 watts, but in reality, it's more like 0.4 watts that we'd be able to get out of this servo. For the Arduino, we can use the servo class to control it, and it would be servo right of 0 would give us full speed reverse. Servo right 90 would be stopped. And if we did servo dot right of 180, it would be full speed forward. The other servo that we have is a 180 degree servo, and we actually have 2 of those in the eLegoo kit of parts. The first one is in the extra kit, and the second one is part of the original eLegoo kit, and it's the one that is used to rotate the ultrasonic sensor left to right. Its mass is also 9 grams. Its no load RPM, not surprisingly, since they're very similar servos, is 0.1 second per 10 degrees. And again, that's 100 RPM. And this one's a little bit more torquey at 1.8 kilograms centimeters, which works out to 1.84 watts. But again, that's overstated, and it's more likely a peak of around 0.45 watts. On the Arduino, similarly, we'd use a servo class, and we'd use right 0 would give us minus 90 degrees, right of 90 would give it centered, and right of 180 would give us plus 90 degrees. Or you can simply think of the servo as going from 0 to 180 degrees, whichever you prefer. So a very simple Arduino program to control a servo. We include the servo class, servo.h. We declare a servo, I call it my servo. In the setup function, you would attach the servo to whichever pin the servo is connected to. And then in the loop function, we'd have our servo value, we'd have some code to figure out what the value would be. And then we want to map the value between the range start and end of that value. So if we were using the controllers from the driver station, they go from basically plus or minus 100, plus or minus 255, 254. We could do that map of the controller value between minus 254 and 254, and that would get mapped to that 0 to 180 degree range on the servo. Then we simply write that. Oh, that actually should be my servo.write servo val. Write that value, the map value to the servo, and that's all there is to controlling a servo on the Arduino. I will fix that in my slide presentation. Unfortunately, it won't get updated in the presentation. So doing an example application of the motor specs. Let's assume that we're going to, or we're planning to do an elevator to lift the cups in the ELIVU challenge. How high do we need to lift the cups? That's going to be an important thing. I've measured the cups and they're just under 12 centimeters tall. So if we said we're going to move them 12 centimeters, how much do the cups weigh? We assume that we want to have the SG90 directly turning a spool. So we want to calculate how large does that spool need to be to get this amount, the necessary amount of movement. And we have to remember that the SG90 is only rotating half of a rotation. So we can do the calculation for how large the spool needs to be, and then we want to know whether or not the SG90 would be able to lift the manipulator that was on our elevator, and determine if that's reasonable or whether we need to switch over to potentially the DG or the continuous servo to turn the shaft at a lower speed. So going through this again, as I said, the cups are about 12 centimeters high. So we need to lift at least the 12 centimeters to be able to lift one cup above the other. The cups aren't very heavy. They only weigh 6 grams. And in fact, in this case, the weight of the manipulator, the gripper, is probably way more than the cup. So the cup's weight is probably negligible in terms of how much we're weighing or we're lifting. And again, we're going to assume that we want to have the SG90 directly turn a spool. So how large does that spool need to be to get that amount of movement? So we have 12 centimeters, and we use our formula for circumference of a circle, which is 2 pi r. But since we're only going 1/2 of a rotation, we need to multiply that by 1/2. When we solve for r, we get that r is 12 divided by pi, which is about 3.8 centimeters. So that would be a spool that was almost 8 centimeters in diameter. So how much can the SG90 lift at that radius? Well, our specs say that it can, it has a stall torque of 1.84 kilograms centimeters, and we want to divide that by 2 for peak power. And then we want to divide that by 3.8 centimeters. So that gives us, and we know that we want to do the divide because if we look at our units, we want to get rid of the centimeters and only have kilograms left. So dividing by 3.8 centimeters is the correct thing to do here. We end up with 0.24 kilograms or 240 grams. Is that reasonable? Well, if we take out the 6 grams for the cup, that leaves 234 grams for our gripper. We obviously couldn't make our gripper out of something heavy like aluminum. If we had another SG90 on the gripper to open and close the gripper, that's another 9 grams off of that. So we're now at 225 grams. I think it's reasonable, but you'd have to pay a lot of attention to the design of that gripper to make sure that you could keep it light enough that the SG90 would be able to lift it. So those are the calculations that we do every year in FRC when we're designing elevators or lifts, or if we're designing the end game for FRC when we're having the robot climb. We do this exactly the same calculations. except in that case, we're also trying to figure out what gear ratios we might use to get the torque in the right range. Are there any questions?